Okay, so in this lesson, we're going to look at arcs and chords. We defined what an arc was on Thursday. Let's remind ourselves of some properties that we know about what arcs and chords are before we build on those. So in a circle, we learned on Friday that we can make an angle with its vertex at the center. And what do we call that kind of an angle? What was our new term? A central angle. When we have our vertex at the center, it's called a central angle. And we learned that it cuts off an arc on the edge of the circle. And let's say that that central angle has a measure of 85 degrees. What did we learn about that arc then? It would also be 85 degrees. That an arc across from a central angle will have the same measurement. What kind of an arc is that? There were two different kinds of arcs that we talked about. A minor arc, because it's a small arc. And so then the rest of the circle is called a major arc. And how do we find how big the major arc is if we know how big the minor arc is? Subtract from 360, because a whole circle is 360. Okay, so then that's what we learned about arcs in the last lesson. And then we're going to bring into this lesson again the idea of chords, which we learned about in our very first lesson of Chapter 9. Somebody remind me what a chord is.
It's a section of the circle from one part of the circumference to another part of the circumference.
Okay, so we go from one part of the edge of the circle to another part. But what kind of a thing is it? A line segment, so it ends at the edges of the circle. So it goes edge to edge on the circle, and it's the segment going through the circle. So it's not the length around the circle, that would be the arc, but it's the segment that cuts through that circle then. And that's a chord that we learned about back in our first lesson. So in this lesson, we combine some ideas with chords and arcs. So our first theorem says in the same circle or congruent circles. What did it mean for two circles to be congruent?
To have the same radius.
To have the same radius. Congruent means the same size, and a radius is what determines the size of a circle. So in one circle or in two circles that have the same radius, congruent arcs have congruent chords, and vice versa. Congruent chords have congruent arcs. So what I'm going to do is make a chord. And then I could make another chord. And if they're the same size, then the arcs will be the same size. And vice versa. If the arcs are the same size, the chords will be the same size, according to this theorem. Questions on that? Our next theorem says a diameter, remind me what a diameter is.
A chord that contains the center of the circle.
A chord that contains the center. So I'm going to go right through the center, edge to edge. A diameter that is perpendicular. What's perpendicular mean? Intersects at 90 to a chord. So here's another chord, and they're going to intersect at 90. It says bisects the chord, so that means that chord is going to be split into equal pieces, and the arc as well. The theorem says a diameter, but really we didn't even use the whole diameter. The theorem really, in my opinion, might as well just say radius, because we didn't even use that other part of it. So if we have a radius that intersects a chord at a right angle, then it's going to bisect the chord and bisect the arc. If we bring into this some other lines here, what are those dotted line segments? What would we call those?
Radii.
They're radii, right? Because they go from this edge to more radii. We also get some other special figures in here. What's special about that? It's a right triangle. Right triangles are going to be really important to you in your assignment today. So we'll do some examples after we get through our theorems, but right triangles and this picture are going to be really important in our problems today. Theorem 9.6 then says, in the same circle or congruent circles, chords that are equally distant from the center are congruent. Or we could say it backwards and it would be true as well. So what we have then is a center, and we're going to go out away from that some equal distances and make some chords. And when we talk about distances, we're talking about the shortest distance, so that when we're looking at perpendiculars there. According to Theorem 9.6, since those two chords are the same distance away from the center, they are to be the same length. Okay? So those two chords would have the same length. Also, putting together with that last idea that it's going to bisect, we really have 4 equal pieces here then. All 4 of those divided sections are going to be equal. Questions on these theorems? All right, let's look at some examples then. All right, so we'll start in the upper left. We are given that AB is 16, OM is 6, so I can label that 6 there. And we're asked for the radius. Where is a radius in the picture? OA is a radius, or OB is also a radius, right? Those are both radii. So we're asked for the length of either one of those. They'd be the same because they're both radii. We're given AB is 16. But what can we do with that in our picture? According to our theorems from today, if we have this perpendicular, AM and BM will be the same length, so we can split that up and get 8s. Now we have that right triangle in there that I said was going to show up in a lot of our pictures today. And so how can I find a third side of a right triangle if I know what 2 of them are? A squared plus B squared equals C squared. So 6 squared plus 8 squared equals X squared, where X is that radius length that we're looking for. So 36 plus 64 is 100. So our radius length is 10 here. Okay, so right triangles in the Pythagorean theorem are going to be really common in your problems today. So look for right triangles where you know 2 pieces. In the next one, it tells us PQ is 10, and likewise, from the last problem, that PQ is broken up into 2 equal pieces of 5s. The radius is 13. Where should I label the radius? PO or QO, either one of them are radii. And we're asked for OM. Once again, we end up with a right triangle here. What is important when we use the Pythagorean theorem? Put the numbers in the right spot. Specifically, which one do we have to be really careful of? The hypotenuse has to be C. So when I plug in then, I'm going to have 5 squared plus X squared equals 13 squared. 13, that radius, is the hypotenuse here. So we need to be really careful when we plug stuff into the Pythagorean theorem that we're putting it in the right spot to the formula. So that chapter 8 Pythagorean theorem is going to keep on coming up for us. So I get 25 plus X squared is 169. Subtract 25, and I get X squared is 144, which gives me then a length of 12. We're going to jump down to the bottom left-hand side, the one that has RS and T labeled in it. And there, the first thing we're asked for is RT. What are your thoughts about RT? 30. How do you come up with 30?
It's bisection.
We have a bisection. When we get that radius perpendicular to a chord, our theorem today told us that it would bisect that chord. So that means both pieces are 15 for a total length of 30 there. Then we're asked to find OM, which is this length here. What are we going to do to calculate that length of OM, that little portion of the radius? Pythagorean theorem again. We've got another right triangle there. So we're going to go x squared plus 15 squared equals 17 squared. Making sure that our hypotenuse is our C value. So x squared plus 225 is 289. Subtracting 225 from both sides leaves me with 64. And I get that OM. The next question on the bottom brings in the idea of arcs. It asks us for the length of arc ACB. So remember when we used 3 letters to name an arc? The 2 outside letters tell us where we start and end, and the middle letter gives us a letter to pass over. So beginning at A rather, passing over C and ending at B, how could we calculate the size of that arc? Subtract. That's a portion of the circle, and we know how big the rest of the circle is. So a whole circle is how big? 360. 360 minus the 220 that is the rest of the circle leaves us with 140 for ACB, A through C ending at B. Angle, AOC. A with its vertex at O, or sorry, did I say AOC? Yep. And out to C. What kind of an angle is that? What's our vocab word for that angle? It's an angle. What kind of an angle? Central angle. It has its vertex at the center. The vertex is O. So we have a central angle. What do we know about the size of a central angle? It's equal to the minor arc that it cuts off. So we just found out that A all the way through C to B is 140. But according to our theorems today, when we have this perpendicular thing happening, what's going to happen to that arc? It gets cut in half. So that means then that each portion of that 140 is going to get broken equally to be 70. So how big is angle AOC? 70. The same as the arc that it cuts off. Okay, so we found that the whole arc from A through C to B was 140 by subtraction, and then according to our theorems today, when we have that perpendicular radius coming in and cutting through it, it's going to cut it into 2 equal pieces. So they're both 70. Central angles are the same size as the arc they cut off. Questions on that problem? The ideas from the last section are also going to be important in today's lesson. Pythagorean theorem and central angles are both going to be important. One more question to look at here. We have 2 chords that are marked as being the same distance from the center. So we have these little tallies on them that say that they are the same distance from the center. So according to our theorems today, what does that mean about those 2 arcs? Or those 2 chords, rather? They're congruent. So our final theorem, 2 chords that are the same distance from the center will be congruent to each other. And if I have 2 chords that are congruent, what do they make, according to our first theorem? Congruent arcs. So these 2 arcs are going to be the same size, which means arc CD is 80. Questions? Your homework is from 9.4, 1 through 13. Again, look for right triangles. If you don't see any right triangles in there, look for adding something in that could make a right triangle. Right triangles are going to be a really big deal in today's lesson.